Good morning. Today we will talk about steady-state probabilities in Markov chains. In the examples from previous lectures, we have seen that when the underlying Markov chain has a single recurrent class, and that recurrent class is aperiodic, then it seems to reach a steady state that does not depend on the initial state. And today we will find methods for computing the steady state. Okay, first of all, we've seen that when there is no periodicity, the probability of going from I to j in n steps converges to a value as n goes to infinity, in examples discussed last time. Moreover, we've seen that, so basically this is under an aperiodic Markov chain. Okay? Moreover, if also there is a single recurrent class, and possibly some transient states, we've seen that these numbers, pi ij, do not depend on I. So let's try to explore this today, and then maybe we can write a formal result theorem that gives us shows us a way how to compute these probabilities. First of all, let's consider this example with three states. There are two LEDs in a room, okay, two LEDs, and this problem is available in your lecture notes, controlled by two switches in the following way. Switch 1 toggles the state of one of the LEDs chosen equally likely at random. And for example, if both LEDs are on and switch 1 is flipped, then if they are currently at 0, 1, they will go to 0, 0 or 1, 0. If they are currently at 1, 1, they will go to 1, 0 or 0, 1, etc. Switch 1 is equally likely chosen as switch 2. If switch 2 is chosen, then both LEDs are turned off. So, or whatever their original state is, the resulting state will be 0, 0. Let's model this Markov chain. Let's model this process, that is, as a Markov chain. The state space that I suggest for this is 0, 1, 2, which gives us the number of LEDs that are on at any given time. Okay, so let's draw that Markov chain and put the transition probabilities on it. So what do you think? From state 0 to what state can I go? I'm at state 0, somebody comes in and flips a switch. Excuse me? Yes, sorry. Adam. No, Emin, I'm sorry. Right. Emin.
We go to 0 if we choose switch 2 or 1 of switch 1.
Right. If we choose switch 1, we definitely go to state 1, right? Because one of the LEDs will be changing states. Okay, and that happens with probability a half. Or if we choose switch 2, we stay at 0. So half, half. Okay, how about from state 1? In state 1, if switch 2 is selected, definitely I go to 0. What else? If switch 1 is selected, I can again get to 0, right? With probability 1/2 if switch 1 is selected. So there's an overall probability of 1/4 coming from switch 1, and with probability 1/2 switch 2 is selected. With that probability also I go to state 0. So overall from 1 I get to 0 with a total probability of 3/4, right, 3/4. And can I go from 1 to 2? Can I go back from 1 back to 1? No, that's not possible. And then this should be 1/4. That's easy, but let's check. From 1 I can only go to 2 if the LED that's currently off changes state, and that requires switch 1 to be chosen and that particular LED to be chosen. The probability of those two happening, since they're independent, it's 1/4. How about from state 2? Can I stay at 2? No, right? Can I go to 0? Going to 0 requires switch 2. That happens with probability 1/2. And there's no staying at 2, right? So going to 1 happens with probability 1/2. Okay, so these, unless you have an objection, these are the transition probabilities. Now, the question tells us, the question asks us to, in part, so this was part A. In part B, the question says, think about the n-step transition probabilities. Okay. What do you think will happen to the n-step transition probabilities, the P to the n matrix in this example? There's a single recurrent class, and it is aperiodic. How do we know it is aperiodic? There's a self-transition. Very nice, Eren. So that self-transition guarantees that all the states have period 1, so it is not periodic. And it's a single recurrent class. Therefore, based on our current previous observations, we expect the P to the n matrix to converge. And to convert to a matrix that has columns that are what? Each column would give us the probability of being in the state that corresponds to this column. So, so basically I expect this column to be the steady state probability of state 0. I expect this column to be equal to the steady state probability of state 1, etc. So I expect something like this. And I haven't really proved it. I haven't really argued or I haven't given the theorem. But suppose the P to the n matrix converged to this matrix. Suppose it did. Then, basically, what would we have? Basically, pi ij, remember, is the limit as n goes to infinity. The probability that xn is equal to j, given xn minus 1 is equal to I. Okay? Now, notice that this notice that currently I wrote it. Wait, I'm sorry. 0 is equal to I. Now I can write the probability that xn is equal to j, right, as the probability that xn is equal to j given xn minus 1 is equal to k times the probability that xn minus 1 is equal to k, right? Conditional probability, total probability theorem or Chapman-Kolmogorov equations by summing over the states. Now, if n is very large, and if steady state, if there is a steady state like this, if the steady state has been reached, then I can argue that this thing has converged to pi j. This also has converged to pi j, pi k, right? And does not depend on time. If that is true, and notice that this is simply the transition probability pkj, if that is true, then the pi k's and the pi j's must satisfy this equation k from 0 to 2 pi k pkj. But by writing this equation for every value of j, 0, 1, 2, I get 3 equations in 3 unknowns. Although, so let's write those 3 equations in 3 unknowns actually. Let's see what we get. Let's write those. Pi 0 is equal to 1/2 pi 0 plus 3 over 4 pi 1 plus 1 over 2 pi 2, right? Pi 0 is equal to pi 0 times p 0, 0 plus pi 1 times p 1, 0, p 1, 0, which is 1/2, which is 3/4, plus pi 2 times pi 2, 0, which is 1/2. Okay, the next equation is pi 1 equals what? Pi 0 times pi 0, 1, which is 1/2. So 1/2 pi 0 plus 1/2 pi 2. That's it. And pi 2 is equal to what? 1 over 4 pi 1. That's it. 1 over 4 pi 1. Okay. So pi 2 is 1 over 4 pi 1. We can use it in this equation to conclude that pi 1 is equal to 1 over 2 pi 0 plus 1 over 8 pi 1, right? That gives us 9 over 8, I'm sorry, 7 over 8. 7 over 8 pi 1 is equal to 1/2 pi 0. All right. Now put it in this equation. What do we get? 1/2 pi 0 is equal to 3 over 4 times pi 1, right? But pi 1 is 7 over 4 pi 0. And plus we have 1/2 pi 2. Pi 2 is 1 over 4 pi 1. But pi 1 is what? 7 over 4 pi 0. Okay. But what? Excuse me?
4 over 7 pi 2.
4 over 7. So is there a problem here? there may be a problem in the fact that I didn't do the numbers right, but, huh?
On the left part as well.
Right. You will see that this equation is not going to help me at all. Okay? So this system of equations contains only two linearly independent equations. Okay, there are three equations, but only two of them are linearly independent. So just by these equations, I don't find a unique solution. There are an infinite number of solutions. However, I'm looking for a probability vector, right? Then I'm looking for the vector pi I that satisfies this set of equations and also whose entries add to 1. So if I combine these equations with the fact that these are probabilities that add to 1, then I can find the result as, in this case, pi 0 is equal to 7 over 12, pi 1 is equal to 1/3, and pi 2 is equal to 1 over 12. Let's check. This is 8 over 12 plus 4 over 12, yes. Okay, so this example is indicating that perhaps there's a systematic way of obtaining the steady state probabilities, which we will now summarize in a theorem. Theorem 2 in the lecture notes. So consider a finite state Markov chain. In this case, let the states be 1 to up to k, where k is an arbitrary finite number without loss of generality. All right. And there's a single recurrent class. Then there's a finite set of values. Let me just write it here. Aperiodic single recurrent class. And then there exists a finite set of values, pi 1, pi 2, up to pi k, such that they are all, of course, between 0 and 1. They're probabilities. And for each value of j, the limit as n goes to infinity, pij n, the probability of going from I to j in n steps, or the ijth entry of the n-step transition probability matrix, ijth entry of the p to the n matrix, is equal to pi j for all values of I. Okay? So it doesn't depend on the initial starting state I. The pi j's are the unique solution of pi j is equal to summation m from 1 to k, right? Pi m p m j. All right, for all j. Together with, it's only a unique solution if pi j's also satisfy normalization. Okay. And we can write this as a matrix multiplication. Another way of writing this thing is pi equals pi p, where pi is the row vector that corresponds to these probabilities. maybe let's not call this A. This is a theorem, and we leave the proof of this theorem outside the scope of this course. But we are going to list now some properties or remarks related to this result. Although we leave it outside the scope of the course, already I think you've seen enough examples where you have a feeling why this result holds. Okay, so these are called global balance equations. And why we call it balance will be clearer toward the end of this lecture. Now, notice that we have pi j is equal to 0 for transient states and pi j positive for recurrent states. In our examples, we've seen that as n grows, the columns corresponding to transient states into the P to the n matrix go to 0. Okay. Now these pi j's are called stationary probabilities because of this reason. Let me just write it here. Pi j's are stationary probabilities because consider getting the process started in various states with these probabilities. What I mean is, suppose the probability that x0 is equal to j is pi j. Right? Then what is the probability that x1 is equal to j? Well, the probability that x1 is equal to j is the probability that x0 is equal to j times p, right, x0 is equal to k, x0 is equal to m, p, mj, summed over all m. But since this is pi j, and we know that pi j's are the solution of pi j p mj summation is equal to, this is pi m p mj summation is equal to pi j, because that's how the pi's are defined, then we notice that the probability that the state at time 1 is j is pi j. It does not change. That's why they're called the stationary probabilities. So if we have an ergodic Markov chain, when it reaches steady states, the states have a stationary distribution. The distribution does not depend on time. The probability of observing each state is equal to the steady state probability pi j of that state, and it does not change with time. So this is the first concept of stationarity that we are seeing in this course, and this is a strict sense stationarity, meaning the probabilities don't depend on time at all. Okay? In module 3 of this course, you will see other notions of stationarity. For example, wide sense stationarity, where we do not insist on the whole statistics to be constant in time, but we say the mean does not depend on time, and the autocovariance is only a function of time difference, etc. So that's a sneak preview of that part. Anyway, so we've understood that these are stationary probabilities. Now, can we also interpret them as time averages in a sample path? Time average fraction of time that state I is observed. So let's call that long-term frequency interpretation. Long-term frequency of occurrence. Consider watching the Markov chain unfold and go through various states in time. Suppose I observe every transition. How often is a particular state visited? How often is state 1 visited, for example? How about I give myself a reward, 1 unit reward, whenever state 1 is observed? And think of n transitions. And I get a reward of 1 whenever there is a state 1 observed, right, whenever state 1 is observed. So suppose suppose my initial state is, I don't know, I. And let's generalize this. I get a reward when state J is observed rather than state 1. Okay, suppose Rij is the total reward in n time units or n transitions, okay? And of course, it is going to be a function of n. So let me write it this way. And in fact, Rijn is a summation. It's a collected reward. It's a summation of ones, right? So, because I get a unit reward whenever j is visited. So maybe I can write it in terms of Rij of k from 1 to n, such that Ij is the indicator function of whether or not I get a reward in time during the time slot or during the transition k. So this is 1 if reward, or 1 if state j is visited, and 0 otherwise. Okay, indicator functions. Now, what is the total reward per time? In other words, average reward over n transitions. Well, I will have to divide this by n. Average reward per time. And it says average reward per time. It is a random variable, right? Now, it can be shown that this average reward per time converges to its expectation. And you have discussed, you have revised the weak law of large numbers in module 1 of the course. In fact, in this case, the strong law of large numbers will hold, such that this average reward per time will converge on almost all sample paths to its expectation, to the expected reward per time. Meaning, the sample paths on which this does not converge have a total probability of 0. Right? So we say that basically the average reward per time converges to the expected reward almost surely. But what is the expected reward? Expected reward. The reward is 1 if state j is visited, 0 otherwise. So the expected reward is probability of getting a reward in a given time slot. But what is the probability of getting a reward? The probability of visiting state j. That is the steady state probability of state j. So this converges to pi j almost surely, or with probability 1. So I can then interchangeably use steady state probabilities or steady state fraction of time that state j is visited. Okay, so of course I didn't do a full proof. The proof is outside, again, the scope of this course, but it follows basically law of large numbers arguments that you can imagine. So then let's, for example, consider the following question in the two umbrella problem. Consider the two umbrella problem. What is the fraction of trips during which I find myself in the rain with no umbrella? You remember there are three states in this problem. And do you remember the probabilities? We can mark the probabilities. But 3 states. What is the fraction of trips during which I'm left in the rain with no umbrella? So during every trip it rains with probability p. Okay. And I'm left in the rain with no umbrella if at the start of my trip I'm in state 0 and it rains. So what is the fraction of trips during which I'm in the rain with no umbrella? Of course, I'm assuming that the process has been going on for a very long time. So after a very large number of trips, what is the long-term average occurrence of this situation where I'm in the rain with no umbrella?
0 times p.
Exactly. We've learned already, we've argued, that the fraction of times that I find myself in state 0 is pi 0. And the probability that it rains is independent of the state, and it's p. So pi 0 times p is the probability that is the fraction of trips during which I find myself in the rain with no umbrella. Okay, then we need to find pi 0. How do we find pi 0 though? We're going to solve pi equals pi p to solve for all the probabilities. Let's remember the, can you quickly remind me the transition probabilities From 0, I get to 2, definitely. From 2, I can get to 0 with 1 minus p. I can get to 1 with p. From 1, I can get to 1 with 1 minus p. Get to 2 with p. Yes. Okay. So let's compute pi equals pi p. How do we do this? Pi 0 is equal to 1 minus p pi 2. Agreed? Pi 2 times p is equal to pi 1 times p. So it turns out that pi 1 is equal to pi 2. Right? And finally, right? I don't need to write another equation because I know already that there will be 2 linearly independent equations. So pi 1 is equal to pi 2, and pi 0 is 1 minus p times pi 2. Pi 0 plus pi 1 plus pi 2 is 1. Let's write everything in terms of pi 0. Pi 0 plus twice pi 2, which is twice 1 over 1 minus p pi 0 is equal to 1. So from here, 1 minus p plus 2 over 1 minus p pi 0 is 1. So 3 minus p over 1 minus p. So pi 0 then is 1 minus p over 3 minus p is what I found. This is the probability of being in the 0 state. Does that make sense? Let's just give some numbers to p. If p is 1, then pi 0 is 0. I'm never left in the rain with no umbrella if it's constantly raining. Does that make sense? Yes, because I will always be carrying my umbrella with me. So my mind is at peace. How about if p is 0? That does not seem to make sense. If p is getting close to 0. So maybe I have a mistake here. Shall we check? Huh? Right. Huh? Right. So if p is going to 0, then, well, it depends on in which state this gets started. So basically, as p is decreasing, this probability is increasing toward, it seems, 1/3, because each state becomes equally likely. As p is increasing from 0 up to 1, the probability first decays and then increases. In fact, what is the worst case situation? Somewhere around maybe a half. Maybe you can explore this. That's sort of beyond really, that's not really the point here. The point here is the long-term fraction of time that I'm in the rain with no umbrella is, and the answer to the question is p times pi 0, which is p 1 minus p over 3 minus p. Okay. So, now that we're talking about the rain, perhaps we can do one of the other examples that we have considered in previous lectures. Again, there was this example with only two states, rain, no rain. And suppose the probability of going from rain to no rain, if it's rainy today, the probability that it's raining again tomorrow, if it's not rainy tomorrow is A. If it's not rainy today, the probability it's rainy tomorrow is B. And these are 1 minus A and 1 minus B. Okay. So let's solve for the steady state in this example. Let me call them 1 and 2 for convenience. Pi 1 equals 1 minus A, pi 1 plus B, pi 2. And pi 1 plus pi 2 is equal to 1. As a result, I find what? I find that basically from here, A pi 1 is equal to B pi 2. So pi 1 is B over A times pi 2. Pi 1, 1 plus B over A. No, A over B pi 1, right? A over B is equal to 1. So from here, pi 1 is equal to B over A plus B. And pi 2 is equal to A over A plus B. Interesting. The probability of going from here to there is A. The probability of coming back is B. And the probability of this state is B over A plus B. In proportion, so the probabilities of states 1 and state 2 are in proportion to the numbers B and A. Is this a coincidence? It is not. Now let's see a few things based on this notion that we've argued here of steady states, the fraction of visits to each state. Okay, so the long-term frequency of visits to state K. Long-term frequency of transitions to state K. Well, we've already shown that that is pi K. How about the long-term frequency of transitions from J to K? Suppose this is state J and this is some state K. And there is a direct transition between the two. Of course, there are transitions from J to other states as well. But what is the long-term frequency of transitions from J to K? Well, we can argue that we make a transition from J to K whenever we're in J, and we take a transition this way. So that should be equal to pi j pkj. But by that argument, if there are two states, 1 and 2, okay, and if the Markov chain is at steady state, okay, and the chain is in this form that we call a birth-death chain or birth-death process, meaning whenever I make a cut here, it splits the Markov chain into two pieces that don't communicate with each other. If there is steady state, the frequency of transitions going this way should be equal to the frequency of the transitions going that way. Because otherwise, there wouldn't be a steady state. For every transition that went this way, there must be a transition coming back, because the only way of going is coming back. All right? So then we find that pi1 p12 should be equal to pi2 p21. So in a birth-death type chain, we can easily use this to compute the stationary probabilities. So let me just write it here. Pi1 times A is equal to pi2 times B, which gives me that pi1 is equal to B over A times pi2, and I'm done. Okay, so for this case, it may seem trivial, but we will be able to apply this to queuing systems where the number of states is quite large and can be infinite, in fact. And this will come in very handy in those situations. We will address that next time.